Yeah, thanks for coming to this second installment. So yeah, last time I talked a little bit about o-minimal structures. If you weren't there, then doesn't matter. I will not use much. And today I want to focus on point counting. So what I mean by this is some theorems, usually in o-minimality, where you want to count algebraic points, rational points on some transcendental sets. Okay, so I'll start with the theorem that started this area, which is the Pila and Wilkie theorem. So maybe many of you know it. Sorry if I'm repeating things for you, but it's a learning seminar. So, so for a subset of R to the n, I'm going to make a few notations. So the most classical one is this XQH. And this is the set of all vectors X in X intersect Q to the n, such that the height of this vector is bounded by H. And this height of a vector, I take, for instance, to be the maximum of the heights of the coordinates, and the height of a rational number is just the maximum of the numerator and the denominator. Now, I want to also make a slightly more general definition, where I'm going to plug in a number here, G and H, and then I'll count all the algebraic numbers. So it's going to be Q bar to the n, such that they generate a field of degree at most G, and again, height is less than or equal to H. Okay, so here already there's some questions about the choice of the height. You can use normalized height or non-normalized height. It doesn't really matter. So just in the kinds of asymptotic statements that I make, the results will not really depend on particularly good choice of the height. So just think about your favorite height. But it's the multiplicative height, where I write big H, it's a multiplicative. Okay, so and I wanted to make one more notation, which is the algebraic part. The algebraic part X alg, this is going to be the union of all connected semi-algebraic curves gamma inside X. I wrote curves here. I could have written positive dimensional, doesn't really matter, but you take all the positive dimensional algebraic things that's contained in X and you put them all in this algebraic part. And this could be quite a complicated set in general. So it could have infinitely many components. Okay, later I'll be talking about o-minimality, and somehow X would be a relatively nice set. X alg does not need to be so nice. Just keep it in mind.
Not definable.
Not definable. It's not definable. In fact, one can usually, in the statements that I make, I'm just talking about X alg to be simple, but one can take some subset which is definable, and wherever I have X alg, you can just take this definable subset, but never mind. Okay, now I can state the first theorem, which is the Pila and Wilkie theorem. So this is Pila and Wilkie. Okay, so this is a theorem about counting the size of this thing. Okay, so we're going to take now X, which is definable. So I'm going to take X in R to the n, definable in some o-minimal structure. So later I'll just say definable, and I mean in an o-minimal structure. Once let me write it. And let me also fix epsilon some positive number. Okay, then the claim is that if I count the number of points in the transcendental part up to height H, then this is going to be less than or equal to some constant depending on the set X and an epsilon times h to the epsilon. Okay, so this is the original Pila-Wilkie formulation. And
X transcendental is a complement of XR.
oh, sorry. Yes. So that's it. Yeah. Thank you. So X transcendental part, that's just X minus X algebra. Okay, the idea is that we don't know how to control the number of rational points in algebraic curves. Algebraic curves can have a lot of rational points, like, you know, if X contains the diagonal, for example, then we're going to have a lot of rational points on it. But okay, otherwise we can give this statement.
Are defined over R or defined over?
The question again?
Right, when you say semi-algebraic curves, what field do they have to be defined?
Well, I mean, the way that I've set it up, I'm just saying the union of all semi-algebraic curves. In fact, you could make a finer statement where, I mean, you could say that it is enough to remove semi-algebraic curves defined over Q in this case. Yeah. Okay, and I wanted to also make one statement for this, more general notation. So now if I take, if I fix G in N, then I'll have the same kind of statement. The number of points in the transcendental part of degree G and height H is also bounded by, now it's C, depending on X, G, and epsilon times H to the epsilon. Okay, so this was the original Pila-Wilkie. This is, I guess, in a later paper by Jonathan. Don't remember which one, but a bit later. And the idea for proving this is basically that you say, we'll reduce it to the previous theorem. We will encode, whenever we have a point X of degree G, we can just kind of add new variables for the coefficient of the minimal polynomial, and then we'll basically be counting these coefficients of the minimal polynomial such that the roots land in X. And you can make this work and you will get the same kind of theorem. Okay, so a few comments about this theorem. Okay, so first thing I wanted to mention is that this is essentially optimal. Essentially optimal asymptotic. So I mean, if you pick some sequence that grows like strictly slower than h to the epsilon for any epsilon, then you can find, for instance, analytic functions on whose graph you will have this many rational points. Okay, so you cannot hope to improve this h to the epsilon to something better in general. Then another important point is that this constant C x epsilon is uniform in definable families. Okay, so what that means is if I remember a definable family means I give you a x which is a subset of say Rn times Rm. I think of the first few coordinates as parameters, and then I can restrict to the fiber for every fixed parameter. So I'll have like a family of sets, and I'm claiming that the same thing will hold with a uniform constant. So I could say that for every x in my family, I'll have a bound like this, and this constant will depend only on the family and not on the particular fiber that you choose. Okay, so that's in my previous talk, I was saying that this is kind of the hallmark of o-minimality, that whenever you get something, you get it uniformly in families. And that plays a very important role also in the inductive proof of this theorem. Okay, so I will not really give the full proof, but I'll try to indicate where this kind of uniformity is very crucial. Okay, and I also wanted to quickly mention that when X algebraic part is not empty, there is something called the block formulation. It's a little bit more technical. I don't want to really give the details, but if you can encounter this reading the literature, basically what it means is that, okay, if there's nothing, if we have no algebraic curves in our set, then okay, we can just count everything. if we have algebraic curves, then what we can say is that all the rational points are going to lie in a union of very few algebraic curves. But there's going to be h to the epsilon algebraic subsets of our set that contain all of the rational points up to h. Okay, and this is sometimes, I mean, in practice, you try to apply the theorem and you do have an algebraic subset, and then you use this block formulation, but it's not very different. I mean, I think if you think about this transcendental part, you are basically seeing the main content of the theorem. Okay, and then, so I said that this is essentially optimal, but there is a conjecture. Is there any question so far?
The conjecture is about the exact rate of growth.
The exact rate of growth here. So I said, if you are working for a general o-minima structure, for instance, in R sub n, this is basically optimal.
Perhaps I mean in terms of maybe log factors or something like that.
Yeah, so if you restrict to some special structures, maybe you can improve, and that's the next conjecture I want to make, so thank you. So there's a conjecture by Wilkie, which is that in the structure Rx, so if we take X to be definable, not in any structure, but for instance, in the structure Rx, but I mean, this should be read as some good structure. I mean, he kind of picked Rx out of his head, but I think like the general belief was that if you have some nice structure generated by natural functions, then you should have a better asymptote. Okay, then we should have the number of points in the transcendental part. And let me even formulate a bit more strong. Let me do it for arbitrary g. On h, this should be less than or equal to some polynomial, depending only on the set x, in g, and in log h. Okay, so the original conjecture was with g is equal to 1. So it was really about counting rational points. But if you kind of look into the proofs and how this kind of thing works, then if you can establish polynomial dependence on log h, then it stands to reason that you should also be able to establish polynomial dependence on g. But anyway, I mean, so I'm slightly cheating. This isn't exactly the Wilkie conjecture. It's a bit stronger. Okay, so this is the conjecture, and I want to just make a kind of a completely formal comment about this conjecture. So this conjecture is kind of equivalent to saying that this constant that we had before, c x epsilon, is going to be bounded by some polynomial depending on x in 1 over epsilon. Let me at least say this implies the conjecture. Okay, because here I said that we have some constant depending on epsilon. Let me put epsilon to be 1 over log h. Then this is going to be just a constant. I mean, this thing holds for any epsilon. Let me put epsilon is 1 over log h. Then this h to the epsilon is going to become 2 or e. And then I just need to know how this thing grows with epsilon. If I know it's polynomial in 1 over epsilon, then it will be a polynomial in log h. Okay, so it's kind of been clear that in this conjecture, basically what, or I don't know if that's the only way to do it, but one way to try to do it is to go through the proof, see where things depend on epsilon, and try to figure out that they, I mean, show that it's polynomially depending on epsilon, and then you would solve the conjecture. Okay, so I mean, this was the idea. If you try to follow the proof, it's kind of hard to make it work. So I'll show you a little bit of the proof, and you'll see why it's hard to work and why o-minimality is not really kind of the correct framework to try to do something like this. Okay, so I'll give kind of the rough idea for the proof.
Can you say a little bit of something, maybe you will, about why the g and the 1 over epsilon sort of play symmetrical roles?
So let me say why g and log h play symmetrical. So the idea is basically in these proofs, it's kind of a transcendence method. So you are going to build a polynomial, you'll arrange that it's very small on the set, and it's going to be so small that it has to vanish on all the points that you care about. And then somehow you will intersect with this polynomial and you keep going. And then, so you get some upper bound that comes from geometry. You're just arranging a polynomial to have small Taylor coefficients or something. And then you get a lower bound from arithmetic. You're evaluating on points. And then in the Liouville kind of bound, you know, if I evaluate my polynomial at an algebraic point, I know that it's either going to be 0 or not too small. And if you think about this Liouville bound, how the height, I mean, the log height and the degree enter in kind of the same way. You know, it's bigger than something like e to the power g times the log height, I guess, is the Liouville lower bound for a non-zero algebraic number. So that's how it enters. Other questions? Okay, so let me give a very brief sketch of the proof. Again, I'm not going to be able to really prove the theorem in this short time, but I wanted to show how o-minimality enters. So, I mean, why one needs this kind of, where o-minimal structures kind of help you to prove something. So the proof idea. Okay, so basically the proof idea, the first thing we want to do is a kind of an important lemma, which state that if x in Rn is definable, then I can cover all of the points I'm interested in. So I'm going to look at all of these rational points up to height n. They're going to be covered by a union of hypersurfaces, algebraic hypersurfaces. So these are just polynomials. And then I'm going to say something about the hypersurfaces. Okay, so what do I want to know? I want to know that the number of hypersurfaces is less than or equal to some constant, depending on x and epsilon, times h to the epsilon. And I want to know that the degrees of all of these p alpha are bounded by some constant that depends only on epsilon. Okay, in fact, I'll kind of say in secret, although it doesn't matter for this proof to work, but I'll mention that this constant is actually a polynomial in 1 over epsilon, depending only on the dimension. Okay, but I mean, for the proof, you don't really need to know that it's a polynomial. Maybe later it would be important. But what we do know is that we can select a collection of polynomials of bounded degree and, you know, h to the epsilon of them, and they're going to cover all the points that we like. Okay, so this is a useful lemma, but we need something a bit stronger. So we need this plus uniform in family. Okay, so what do I mean by uniform in families? Here I said that the number of points grows like h to the epsilon, but with some constant that depends on the set. And now I'm saying if you have a family of sets, then you can do this uniformly. This constant is not going to depend on the particular fiber that you pick. Okay, and that's kind of crucial for the induction. And then let me say quickly how this lemma implies the theorem.
You must need something about the constant in terms of epsilon too, right? You need Cx epsilon is not too big in terms of epsilon.
In terms of, if you want to get Wilkie's conjecture, if you want to get Pila Wilkie. If you want to get Pila Wilkie, you don't care. You just want to say.
Pila Wilkie don't care. Yes.
Yeah, for Pila, what I really will need later for Pila Wilkie is this. I will need to know that actually in this choice, but you see, this is a very universal thing, and it's been understood by Pila and Bombieri how to choose this thing, and it's roughly 1 over epsilon 2.
But for Wilkie, you also need the Cx epsilon, right? Not just the degree.
Yeah, I mean, for Wilkie, you need a bunch of stuff, but I mean, just out of this proof, I mean, the important ingredient would be this thing. Yeah, of course, you will also need to analyze these constants. And okay, now let me say why this lemma that I wrote over there implies the whole theorem. Okay, so basically we want to count this xqi, so let's replace x by each of these intersections. X intersect p alpha is equal to 0. Right, so I'm interested in the rational points here. And I said they're all going to be in one of these guys. And I don't have too many of these. I have h to the epsilon of these. So I might as well replace x by these. And now I should just prove the theorem for each of them. That's the idea. And now I'll induct over dimension. Okay, so there are a few things to check. The main thing to check is that really the dimension drops, right? Because I mean, I cut X with a polynomial, maybe it's contained. And this is where this assumption of not having an algebraic part comes in. Okay, so in fact, you can show that if you're not in the algebraic part, then you can arrange things so that these intersections will be proper and they will drop the dimension. So these are really of smaller dimension. But another very important thing here is this uniformity in families, because basically now I want to get a bound for these things. And if I have a bound that depends on P, then it would not be good, because I'm taking H to infinity, I'll be taking all sorts of different polynomials. And if for each of them I have a different constant, then I will not be able to control it. The important thing is that all of these guys kind of come from one family, right? It's a polynomial of a fixed degree, depending only on epsilon. So I can encode all of these sets as fibers of a single definable family. And therefore, in this lemma, I can kind of repeat. The next time I'm going to use this lemma, I'll have again a uniform constant. Okay, so that's the very important thing here. That's why I needed this D to be D of epsilon. Right? I want to get this uniformity. I want to know that it's only, I mean, the degree kind of does not depend on the particular set that I chose. So just if we are thinking for a moment about Wilkie's conjecture, this is where, I mean, things really deeply break down. Okay, because this is a definable family when I fix the degree. Then if I'm going to try to take epsilon to be 1 over log h, then this D is going to be log h. Now the degree is not going to be a constant. Now the degree is going to depend on h. So, I mean, this thing is not going to be in a single definable family. So, I mean, here things really break down seriously if you try to go from the Pila-Wilkie theorem to Wilkie's conjecture. Okay, so, but let's keep with the original theorem, which is already interesting enough.
In the lemma, you have XQH or X transcendental? You want the full?
Well, I mean, in fact, you can interpolate all of the algebraic points like this, I mean, in the lemma. But okay, when I make this step, if I'm not in the transcendental part, I'm not going to be able to guarantee that this drops a dimension. So somehow in this inductive step, I want to replace this by this and induct over dimension. I cannot guarantee that I will be able to do it if this intersection is not of a smaller dimension, and that can happen if it's algebraic. Suppose X was just algebraic, then certainly the lemma is true because you just take a polynomial that vanishes on X, but I mean, clearly you cannot go anywhere with this.
So then how is X relevant? What if you just take X equals R to the N?
Well, if you take X is equal to R to the N, then okay, I mean, maybe in this lemma, I do need the dimension, thank you. Maybe I do need that the dimension of X is less than N. Right, thank you. Yeah, I mean, it will not be a problem for the theorem because if X is all about the N, then it's all the algebraic part. So you can kind of always throw the open bits of your set because they are full dimension, they're always in the algebraic part. So we kind of always can assume that we're dealing with a proper hypersurface. But yeah, I mean, formally for this lemma, you do need this assumption. Thank you.
So the precise statement that you induct on is some kind of Pila-Wilkian family, so the block form, or what is the?
I mean, you need to induct on Pila-Wilkian families. If you want to prove the block form, then you should induct on Pila-Wilkie in block form. But yeah, I mean, the Pila-Wilkie itself is uniform in families, and I mean, and you should prove it in the stronger form if you want to do an induction.
But all of these P alphas in the lemma come from the same family, or?
Yeah, because they are just polynomials of a fixed degree, right? So you can kind of say, okay, let me take as parameters all the coefficients of a degree 10 polynomial, and I have a single family.
They're non-zero. The numbers are not.
Yeah. Okay, I mean, Wilkie is saying these are non-zero, otherwise my lemma would be correct but stupid. So yeah, so P is okay, you understand. P is not zero.
But I understand, so somehow when you apply the induction and you get to the smaller set, you get some families of polynomials associated to the smaller set.
Yeah.
But each different thing you intersected with has a different family. Do you need some compatibility? Different.
I don't need compatibility, but I will get like bigger and bigger families. So now, I have a family where I see all of these fibers. And the next step, I want to intersect with another guy, with a Q alpha. So I'll add also a bunch of variables now for all the coefficients of Q alpha. and they'll have a family where it's X intersected with P alpha, intersected with Q beta.
Right.
This will have like fibers of one dimension lower unless you're in the algebraic part. I mean, you keep making,
But somehow the betas, like the degrees of the Q betas are bounded independently of alpha.
yeah, I mean, they're in fact depending only on epsilon. In this lemma, there's no, I mean, some of the degrees don't depend on anything. Yeah. I have a question. Very good questions today. I should take a pencil and make notes to correct my mistakes here. I'll watch the video later and see all the mistakes that you guys pointed out. Okay, so now, okay, this is kind of how the proof works, but the interesting thing maybe is this lemma. I mean, where does this come from? So I will not show you completely, but I'll say what the ingredients are. Okay, so how do we prove the lemma? Okay, so there's kind of two ingredients to this proof. One is very classical, it's due to Bombieri and Pila. So what Bombieri and Pila showed, Bombieri, Pila, they basically showed the case where your set X is given by the image of Q. Okay, so if my X is just, I can kind of parameterize it as the image of a cube of the same dimension with I want to say that the CR norm is bounded by 1. So this is CR norm. So pick your favorite CR, say the maximum of all the derivatives up to order R on this cube. I is just the interval 0, 1. Okay, and I should say what is R. So where R, again, depends only on epsilon. And again, I'll say in secret, although for Pila Wilkie it doesn't matter, that this R is going to be a polynomial depending on this dimension. Let's say that this was in Rn. The polynomial depending on n in 1 over epsilon. Okay, so we are trying to say that all the rational points can be covered by few hypersurfaces. And what Bombieri and Pila showed is that, well, if your set is kind of simple, if it's the image of a smooth map, a CR smooth map with unit norms, then you can do it. Okay, so this is a completely elementary exercise in estimates on determinants, very beautiful.
This is literally what I would see if I look at the paper, and I thought the paper was about curves and
Yeah, I mean, yeah, Bombieri and Pila did curves. I don't know who did the higher dimensional generalization. Maybe Jonathan did somewhere. But I mean, you would see kind of the key idea even if you look at the curve case. So there's a certain, if you want to know whether points are interpolated by a hypersurface, then you can write a certain determinant and check if it vanishes. When you write the determinant, you know, because you're plugging in algebraic numbers, rational numbers, then you have an a priori lower bound. The determinant either vanishes or it can't be too small because just you plug, because it's a rational number. And you can arrange, I mean, in this situation, you can see that actually the determinant has to be very small. It's so small that it will have to vanish. And therefore, they're all interpolated by rational numbers. And you basically need to subdivide this cube into smaller cubes of size, like size h to the epsilon, 1 over h to the epsilon. So you cut up your cube into h to the epsilon small cubes. And then on each of them, you can show that all the rational points are just interpolated by a single polynomial of some fixed degree, right? And I mean, to do that, you need to do Taylor approximations up to roughly the same smoothness order. So you need all derivatives up to the roughly the same order to be bounded. So this is a technical lemma, but
so if I wanted to look at the number of rational points on such a hypersurface, I won't be able to continue the induction. I'll be able to just get one step and not go on, or what is the point?
I mean, so the lemma will tell you, you are able to construct all of these polynomials. So the polynomials kind of catch all the rational points. And now if you want to continue, you should intersect your x with each of the polynomials and now somehow go on. But now your x is already not the image of a cube. So it's not clear how you go on. But I mean, at least this kind of gives you the first step of the induction. Okay, so, but if you want to really do an induction, I mean, we should get rid of this assumption. Right? I mean, this is in the case that you are just given by the image of a smooth map. And the general inductive statement is for an arbitrary set, then you can do an induction. So the question is how to go from this form to something more general, and this is where some kind of a deeper result of o-minimality is needed. So we need one more lemma to finish the job, and that's Yomdin-Gromov. Okay, so I mean, Yomdin-Gromov is really a lemma in semi-algebraic geometry, but I mean, as is often the case, a lot of these lemmas from semi-algebraic geometry you can generalize to o-minimality. Okay, so Yomdin proved a certain lemma for semi-algebraic set, Gromov improved it, still for semi-algebraic set, and then Pila and Wilkie generalized to o-minima structures. And the lemma is as follows. So let's fix an order of smoothness. And then, okay, and let's say, and x in 0, 1 to the n definable. Okay, then I claim that I can write x as a union over alpha of the alpha of I in x. So I can write these smooth charts where P alpha R is less than or equal to 1. Okay. So this is almost the lemma. But as usual in o-minimality, there's another important ingredient, which is uniformity in families. Plus the number of these phi alphas is uniform in families. Okay, so what this set says, first, let's do it for one set. You take a definable set, it could be very singular. And we are saying we can kind of put smooth coordinates on it. Okay, we can, if it's a set of dimension 3, I can just map 3-dimensional cubes into the set, and I'll cover the set with these 3-dimensional cubes. You can even make this, disjoint if you used open intervals instead, so
Closed.
Here X is just an arbitrary definable set, but I should take this I to be open in this case. I'm sorry. So here I is 0, 1. But I mean, this doesn't really matter. But yeah, if you want to make, if you want to really cover the set exactly, then it could be any definable set, but it should be an open interval. And this should, if you did go to the previous talk, this might remind you of these cell decompositions, where we said that any definable set you can cover by cells. And the cells are kind of similar to products of open intervals that are kind of moving around. Okay, somebody asked me if one can make the derivatives of the maps that define the cells, it was you, if you can make them of bounded derivative. And I said this was a deep question. So I mean, here it's something in this direction. So here we are not exactly saying they are cells, they are results where you can take these things to have a cellular structure as well. But the point is you can like arrange that all the derivatives are bounded up to a given order, and yeah, and you cover the set. Okay, so
does that mean that you can also control what goes on at the boundary of the cube?
I mean, it goes all the way to the boundary. If you want, you know, because this is o-minimality, you can say, okay, let me first cover inside the cube. Then let me later cover just the walls of the cube separately. Then outside the cube, let me invert into the cube and cover that. So, I mean, you can kind of cut things up and control separately.
But you don't need to use phi that have bad behavior as you approach the boundary.
No, I mean, phi really has a bounded norm. I mean, it's a, you know, the R norm is bound. So all the derivatives are bounded by 1 all the way to the boundary. if I didn't have a one here, if I just said they're finite or something, then it could explode the boundary, but here I'm really getting one. Okay, so this is, for me, when I saw it was a very mysterious theorem. For example, because I thought, okay, I'm working with analytic sets. Why are we moving to this strange CR category? I mean, if things are analytic, then surely, I mean, you can cover it with analytic maps. For instance, let's say I have an analytic, kind of a compact analytic set. Let me just desingularize it. Then I have a proper non-singular model for it, and I can just cover it with, perfectly nice holomorphic functions, finitely many. But the point is that this will not work uniformly in families. Okay, so you can think, for instance, if you take a family of hyperbolas like xy is equal to epsilon, let's say inside the unit polydisk, and you try to cover it with holomorphic maps, you will see that you need more and more maps. Okay, the maps that are defined on a disk, they cover an area of like bounded hyperbolic diameter. And when these things degenerate, the hyperbolic diameter can go to infinity. So it's really not possible to make this statement if you're working in the holomorphic category, or if I put here an analytic norm. Let's say I said I want all derivatives to be bounded by one, it simply wouldn't work. Okay, so it works for any fixed finite R, but you cannot take R to be infinite. Okay, so this uniformity is kind of where the Yom-Ding-Gromov lemma is really doing something. Okay, so with this lemma, you can kind of finish the proof. Okay, so now whenever I'm giving a set, I can cover it in this way, and then I can reduce to this Bombieri-Pila step, and then this will give me this lemma. Okay, this is roughly how things work. And once again, if we were to try to do the Wilkie conjecture and like work our way back through everything, we would really need to understand how this number depends on R. Okay, because there was a D, and this D was related to my R. I mean, my R was depending on epsilon, and now I want to cover with R times smooth maps, and I'm telling you that this is not some number that's independent on R. I mean, you cannot do it with R is equal to infinity. So it really grows as R tends to infinity, and you would like to say that it grows polynomially with R. Again, so I mean, in all steps of this proof, you somehow need to improve something if you try to do it for Wilkie's conjecture. Any questions?
Can I just go back to the statement of the theorem, and suppose I redefined X algebraic to include
Which theorem?
the main theorem.
The main theorem. So Pila Wilkie.
Pila Wilkie, yeah.
Yeah.
Suppose I replaced X algebraic by unions of all connected semi-algebraic surfaces instead of curves.
Mhm.
I get a stronger version of the theorem, like fewer.
I mean, if you said only union of surfaces, then it would mean that you are allowing your set to contain curves.
Mhm.
And
So should
you
you
claim something.
Yeah.
Yeah, but this would be a wrong theorem. Of course, you could maybe you can say if these curves are of genus bigger than one, or one can maybe imagine that if you exclude only, which curves do you need to keep? Maybe about curves, we know which of them can have a lot of rational points and which don't, so you can kind of think about that. But these results are usually not uniform, so you should be kind of careful. I'm not sure if there is a good statement where suppose that you are allowed to exclude all the curves that are of genus higher than one. Will this give you a bound? It depends on whether you have uniform bounds for the number of rational points and curves of positive genus. So I'm not sure off the top of my head.
Sorry, but I'm a little bit confused because I thought in the theorem we were removing all semi-algebraic curves.
Mm-hmm.
Now I want to remove all semi-algebraic surfaces.
Well, in fact, if I remove all semi-algebraic curves, I also remove all semi-algebraic surfaces because every surface is a union of curves. So it's really kind of I remove everything that's semi-algebraic of positive dimension gets removed when you remove all the curves. But not the other way. If you just remove surfaces, then you do keep curves, and then it could be a strictly stronger theorem. Okay, so now let me talk a bit about some kind of stronger results where we can get Wilkie's conjecture. So this is called sharp o-minimality. Okay, so basically, in order to be able to do that, we have to go through all this machinery of o-minimality, but be able to keep track of how things depend on the degrees. Okay, so you have to kind of introduce some complexity on your sets and say that things are not just finite in families, but how, I mean, if I have a family where I intersected with polynomials of a given degree, how do the constants then depend on the degree? Okay, so the kind of systematic way of doing it is I'm going to think about my structure like just a collection of definable sets. So it's the power set of R, R2, and okay, so this is like the collection of definable sets. These are all the definable sets in my structure. And then basically when you have an o-minima structure, this collection is closed under various operations. Okay, so it's closed under union, intersection, projection, complement, and you can define o-minima structures like that, but now we are going to say that we are going to put on these sets some notion of complexity, and I'll say how this complexity changes when you make these logical operations. Okay, so the way I put the complexity on my sets is I'm going to fix a filtration, omega fd, so it's filtration with two indices, format in degree, they are both integers. So I call this a filtration when the union of all of these omega fd's is equal to everything. Okay, so every definable set has some format and degree, and also it's increasing. So omega fd is contained in omega f plus 1d, and it's contained in omega f d plus 1. Okay, so the way to think about these filtrations is kind of I'm going to assign a complexity to my sets, and it's really thinking about how complicated is the formula that describes the set. And I can have a lot of different formulas that describe the set, and you can't always choose which one is like a minimal. So instead of kind of trying to fix a minimal representation, I'm just saying, okay, all the things that are represented by a certain kind of formula are going to be this part of the filtration, and it's okay, there's two kind of different variables. So you should think of the degree as something like all the degrees of the functions. So let's say I wrote a formula involving some polynomials. This d will be all the polynomials that appear in the formula. And the length of the formula, how many quantifiers you had, how many and or, that kind of thing is going to go to the format. So format is kind of like a dimension. It's measuring some like the number of operations that you did, how many variables the set involves. And degree just measures the degrees of polynomials that appear in your formula. Okay, but that's kind of vague. Let me just tell you what are the whole point of this formalism is that you can make it kind of precise. So let's say I have A and B in Rn, and okay, A is in omega f dA, and B is in omega f dB. Then I'm going to say that A union B and A intersection B is going to be in omega f dA plus dB. Okay, so when you intersect or take unions, you sum up the degrees. I'm going to say that if I do Rn minus A, so if I take a complement, or if I take a projection of A to Rn minus 1, this is going to be in omega f dA. So this does not change format and degree, where I take a complement or when I project. But so far, nothing increases this format. I mean, somehow, if it was like this, then the format would be bounded. There's one more operation in o-minimality that you have to allow, and this does increase format, and that's adding a variable. Okay, so if I do R times A or A times R, then this is going to be in omega f plus 1 dA. Okay, so if you kind of built your set from a sequence of these logical operations, then the format is really remembering how many dimensions you added. You might have added dimensions and then projected, and this format will remember that you are actually a set in some high dimension that got projected down. Yes.
I'm just curious, when you intersect, Bezier would suggest you multiply the degrees. How do
Yeah.
you reconcile?
I mean, it's because eventually my bound is just a polynomial in D. I mean, it's not quite as sharp as, I mean, Bezier really gives you the correct number of intersections. I'm just going to tell you eventually that something is bounded by some polynomial in D. And so it kind of works out that you can even take the sum here and not the product, but it's not a very crucial difference. I mean, you could have taken product, then you'd end up with the same theory, more or less.
I'm just curious, like if you apply this to actual like algebraic varieties inside R to the n, which I assume is sharply or minimal, and F is just actually things in Rn.
So I mean, if you want to have like a sharply or minimal structure, in this sense, then somehow eventually I'm going to have a theorem that says you have a bounded number of components. Maybe you would like this bound to be D. But I mean, the way I set it up, it's going to be D to the dimensions. So I mean, even if, I mean, here you build something and the degree kind of stay the same, but eventually the bound is D to the dimension, then it kind of all works out.
So is the point that like your format only gets so bad in any given proof or theorem or whatever, so you sort of don't really care about.
So yeah, I mean, the idea is that if you're doing something like semi-algebraic geometry or o-minimality, but even semi-algebraic geometry, and you're really increasing the dimension, then dependence is very bad. It's like doubly exponential even in the algebraic case, and we are not hoping to control it well. The idea is that this format I'm always going to assume it's bounded by something, and I'll just increase the degree. And if you hope that on the degrees, you can get a better dependence. That's kind of the philosophy of, I mean, why we set it up like this. So, okay, so far I introduced kind of a filtration, and I just gave some closure axioms. So every o-minimal structure, you can put a filtration like that, right? You just decide what format and degree you want to give to some sets, and then just close up the filtration under all of these rules. It's not, I haven't introduced any restriction. Okay, so there is no restriction yet. And the restriction comes from o-minimality. I mean, these are kind of all the axioms of kind of, I don't know, a structure, but I haven't said anything about o-minimality yet. So for o-minimality, for me, it's always o-minimality over a field. There's two more things. There's the field structure, and there is some finiteness. So I have two more axioms that have to do with the field structure and with finiteness. So the first of these is that if I take a polynomial in n variables, then the set of zeros is going to be in omega n in the degree of the polynomial. Okay, so kind of this filtration agrees with the usual filtration that we have on algebraic sets. The format of a polynomial is the number of variables, and degree is the degree. Okay, and then one final thing. Let's see if I can fit it here. So now I'm going to take X in R. So o-minimality will tell you there are finitely many connected components to X. Okay, that's the axiom of o-minimality. And now we are going to make it more explicit. We are going to say that the number of connected components is of X is less than or equal to some polynomial in F and the degree, where this is some, so these polynomials are kind of part of the structure. So when I say that the structure is sharply or minimal, I'm saying there's a structure, there's a filtration, and there's a sequence of polynomials such that this holds. Okay, so it means whenever you have a set of format F and degree D, you can control, if it's a subset of R, you can control the number of connected components, and it's going to kind of be some polynomial depending on the format, evaluated on the degree. Okay, and even though I impose this condition only on subsets of R, it's going to imply kind of good finiteness results for all dimensions, just like it does in o-minimality. Also in o-minimality, we just impose a finiteness on R, but then we get bounds for all kinds of things, like decomposition in all dimensions and so on. So I'm claiming that this happens as well. So once you have all of these axioms, then the number of connected components for any set is going to be bounded by polynomial in the degree. The sizes of the homology groups, the, triangulations, whatever you can do in o-minimality, you can kind of try to do it effectively.
So when you say it's for any set, is it in terms of the degree and the dimension of the set?
So, every set has a format and the degree. In fact, there's a small extra axiom where I say that the format is always bigger than the degree. That's somehow important, but it's just if you kind of think about how I set it up here, whenever I increase the dimension, I also increase the format. And then I claim that there is, so if you know the format.
Format is bigger than the degree, that's not what you meant.
No, I'm sorry, I meant that the format is at least a dimension, sorry. So I'm not going to, I don't want to have sets of arbitrary dimension and small format, but that's a technicality, so I wanted to sweep it under the rug. Other questions? Yeah.
So in the case of the theory of real closed fields, where you can very explicitly write down all of the definable sets, can you be explicit about what satisfies these axioms?
Yeah, so you can construct, so it's a question, is there any example of these axioms? So for example, is R-alg just a semi-algebraic set? Do they satisfy these axioms? And you can put filtration on them that will satisfy these axioms. And it's basically by the kind of effective proofs of Tarski's Heisenberg. So there is a way that you can, in fact, there even the format can be taken to be the dimension. So, part of the complication is that we do not know how to take the format to be the dimension in general. And trying to mimic the semi-algebraic case was part of the reason why this theory was kind of delayed for a long time. Because we had only one example, which is the semi-algebraic case, and there you can take format to be dimension. So we were always trying to take format to be dimension, and then we simply don't know if it's true. We know of no other example we're able to do it. So, yeah.
So what's the obstruction or what?
Really the obstruction is that you need to, in the semi-algebraic case, you have quantifier elimination. So everything is really given by quantifier free formulas. And so you can basically measure complexity of the set by the complexity of these quantifier free formulas. Okay, but in other structures, we don't know how to construct these quantifier free formulas efficiently. Okay, it really boils down to Thom's lemma. So there's a lemma called Thom's lemma that is very helpful in semi-algebraic geometry for defining the cells. So when you're doing this definable cell decomposition, you can use Thom's lemma to define the cells with a very efficient formula. And there's nothing like this Thom's lemma that we know of for other structures. And in fact, some structures don't even have quantifier elimination, don't have, so it's kind of when you get to more complicated structures, it's not clear if you can expect something like this. Other questions?
So if I understand the second to last axiom, if P has no solutions, then what happens?
These are all only upper bounds. So I'm just saying the number of conic components is bounded, but yeah, it's not like Bezout's theorem where you can really predict. I have dreamed that, maybe you can somehow build a theory where it would be a precise prediction for the number, but o-minimality, you are cutting things with inequalities, things can run off to infinity, so it's difficult to expect something like this. Other questions?
So certain interval, I guess the omega FD contained in is some set closed on lexicographic ordering or something, or this stuff. So intervals even in R,
Yes.
they're all in omega 1, the number of components or something like this.
Yes.
Units of intervals.
Sure.
But I guess certain set units of intervals could be in omega something high, some of D being small, and that's important.
It really depends on how, if in your language you included some magical function, the J function, and now you say, well, let me restrict it to the imaginary axis, and let me look at its zeros, and maybe it turns out that it has a million intervals. Then, this kind of million intervals are suddenly defined with quite a simple formula, right? So this million would come in, but somehow if your set is sharply amenable, it means that things can't be too wild, right? If you know the degree, then you know that it can't have too many intervals, right? But that's something to prove. Other questions? Okay, so I wanted, before stating something about point counting, I need one more definition, unfortunately. should I do it? Maybe let me do it here because we have this conjecture. Yeah, then ideally I would like to say that there is a large sharply or minima structure that contains all the functions that we care about, and Wilkie's conjecture holds in that structure, and that would be ideal. We are not quite there yet. So first, we need one extra assumption when we try to deal with Wilkie's conjecture. And the assumption is, so I'm going to make a definition. I'm going to say that if I have this kind of structure, which is sharply or minimal, it has sharp derivatives. Basically, if I can take derivatives with good control on the degree. Okay, so what it means is that if I take f, which is in omega fd, so formally that means the graph of f is in omega fd. F is, let's say, a function from Rn to R. Then I want to say something about the derivatives. I want to say that for every alpha in n to the n, if I take this alpha derivative restricted to where it is defined, this is going to be in omega O1 of f and poly f d and alpha. Okay, so it's a bit complicated. Let me explain. So this means just the format of it's just my asymptotic notation. It means, sorry, OF of 1. It's kind of it's something, it doesn't depend on anything, but it depends somewhere on the format. So I'm saying if you took a function of some format, the derivative will have some format. I don't care what it is. But what I do care is that no matter which derivative you took, the format is independent of the derivative, and the degree grows polynomially with the derivative. Okay, so this is something that I don't know how to prove in a general o-minimality. You can always define these derivatives. They're always, you can define it with epsilon and delta. You can define the derivatives. But as you try to write the epsilon delta definition for higher and higher derivatives, you will need more quantifiers or more complicated kind of expressions. So the format will grow. And then we don't know what to do. So we want to know that when you take higher derivatives, only the degree grows. So this you can expect to hold when your structure is made out of solutions of differential equations. If you kind of have solutions of differential equations and you derive them, then you basically just get algebraic expansions in the original variables. You don't need to kind of include more and more variables to express them. So we do have a structure that has these properties. Okay, so there is what is called the R restricted Pfaffian. So that's a certain structure. This is a sharply or minimal. So this is a structure that was introduced by Chovansky. So these are solutions to certain triangular systems of differential equations. I will not have time to define it, but it includes, for instance, the exponential function restricted to compact intervals, and a lot of other functions. And basically the thing what I wanted to tell you about this restricted Pfaffian structure is that it is sharply or minimal, and it does have sharp derivative. Okay, so there's a theorem which is formally by Vorobyov myself, but it's really based on a lot of work by Gabrielov. So Gabrielov and Vorobyov studied these restricted Pfaffian structures a lot, and they proved a lot of things about them, but they did not quite prove sharp or minimality, and we kind of managed to prove a certain result for this structure with Vorobyov, and that was kind of the motivation for inventing this sharp or minimality. And it's basically saying that this R restricted Pfaffian is sharply o-minimal, and plus it has sharp derivatives. So that's the part about sharp derivatives is a bit later. It's by myself and Novikov and Zach. Okay, so we do have at least one example of this axiomatic framework. Okay, there is a structure that has.
Why do you need to truncate why do you need to restrict your
So the Pfaffian structure, the Pfaffian functions. So I mean,
you understand why you would like if some kind of PDE or something to hold, you sort of understand holding maybe you sort of then change differentiation to multiply by something. But what is the restriction?
so I mean, in fact, this Chovansky defined them also when they're not restricted. And everything I say is supposed to hold also when they're not restricted, and it's just not fully written yet. So in fact, I believe that even without this restriction, everything works. But I mean, this is what's already in the literature, and it's enough for proving the conjectures. But yeah, I do think that this restriction is not really. It does create some serious technical difficulties. So when you try to work with the unrestricted one, when you try to you have to describe the closure of sets in the boundary. So if you are restricted, you have some differential equations that extend to the boundary. And then it's kind of easier to describe the closures of sets. And if you are in the unrestricted, you are not restricting to a compact interval, you have to when you're taking closure of set, you have to somehow extend your equations to infinity. This is something that Patrick Speisiger has worked on, and I mean, everything does work, I think, but it's more complicated. But let me finally state the theorem, the main, the end of this story about the Wilkie conjecture. So a theorem by myself, Novikov, and Zach. Okay, so if the structure, S omega is sharp o-minimal with sharp derivatives, then Wilkie's conjecture holds. In a quite a strong way. So if X now is a set of format F in degree D, then the number of points in transcendental part GH is going to be bounded by a polynomial depending only on the format in the degree of the set G and log H. Okay, so in this case, you have Wilkie's conjecture, and you even have it stronger. It's not just depending on the set, it's even depending polynomially on the degree of the set. Okay, and in fact, even though this is for restricted Pfaffian, you can actually deduce from this theorem the full Wilkie's conjecture. Okay, so if you remember what I said about Rx being a model complete, I mean, you can use this fact that it's model complete to say that whenever I'm counting in Rx, I really have just a projection of a quantifier free set, and then I can restrict it to a sufficiently big ball, and I can count in that restriction. So there's a certain trick where you can go from this theorem to the full Wilkie's conjecture, even for unrestricted exponentials. But okay, that's the main theorem. I'm out of time, so well, I'll just say that, I mean, to prove this theorem, you kind of go through the proof of Pila-Wilkie, and now you kind of try to keep track of how things depend on the degree at every step. And the really hard part is this Yoam-Dingromov lemma. It's a complicated lemma. You have some dependence on the smoothness order, and we have to analyze how that depends on the order of smoothness. And I mean, there we don't exactly recover the lemma. We have this technical weakening dilemma. So there are some details hidden in the background, but basically you use this notion of complexity to keep track of how things depend on the degree throughout the proof, and eventually you end up with this polynomial dependence on log h. Okay, sorry for running over, and yeah, stop here.
Questions?
So suppose that you keep the definition the same, but you remove restriction that P F of D has to be polynomial. So it's either just some function or has some other order of growth bound.
Mhm.
And you get a priori some family of weaker notions. Can you say anything about like, are these trivial? Are they equivalent to o-minimality? Are there any further examples of that?
Yeah, so even in my notes, I do have a bit of so when we can't get this sharp o-minimality, okay, you can try to say, can I give some effective bound, like, some function, not polynomial? And I do know that you can do it with a much larger structure. So there's something called Noetherian functions, which includes kind of all solutions to nonlinear equations. So it includes sections of Gauss-Manning connections. It includes, modular functions, anything that kind of solves a nonlinear ODE. They all belong to this kind of structure where you have some effective bounds. And yeah, the question is, can you improve it to a polynomial bound?
Yeah, so I guess it was related to that. Are there any structures that you expect other than the Paphian ones to satisfy this property, this sharp minimality with sharp degree?
Yeah, so there is this structure that's generated by Noetherian functions.
So for this one, you expect it.
And yeah, this was conjectured by Chovansky in the late 70s. He conjectured that it's effective. So he conjectured that when you write systems of equations with Noetherian functions, you can always give effective bounds. But I proved that his conjecture quite recently, and I do expect that actually it should all be sharp, but it seems like quite different.
Questions? All right, let's thank Gal again for a very nice